Hey guys, today we're going to talk a little bit about a series. Before we get to talking about what a series is, we're going to talk about something called factorial. So, sometimes factorial people get a little bit confused, and sometimes they see this and instead of saying 5 factorial, they say 5 because they think it's just a really excited 5, but it's not. So, here's what factorial is. If you see a number with an exclamation point after it, that's factorial. Now, you can only do factorial if that number is a positive integer. So if n is an element of the integers and positive. Also, we're going to define 0 factorial as 1. So that's something that mathematicians tend to do, is just define one case. So that way, when you start doing proofs that involve something like factorial, or here in a moment, I'll give you an example that involves primes. Um, Sometimes those proofs just don't work unless you define something as being a certain way. So, for example, if we talk about the definition of a prime number, it's any number other than 1 whose factors are only 1 in itself. Well, so all of the stuff that's true for prime numbers isn't necessarily true for 1, even though the only factors are 1 and itself, 1 and 1. There's still a lot of proof things that don't work that way. So that's why we have to define 1 as not being prime. Anyways, so factorial, it doesn't come up too often. We'll look at it a little bit later for a way to look at binomial expansion. But the best way to find it is, first of all, so n factorial is n times n minus 1 times n minus 2 all the way down until you get till 2 times 1. So like if we were looking at 5 factorial, that would be 5 times 4 times 3 times 2 times 1. So figuring out that this guy right here is not that difficult. We could just pop it in our calculator. But when you have several factorials all together in one equation, it can get to be kind of a pain in the butt if you want to have to keep punching all of those numbers in. So your graphing calculator does have a way for you to do factorial. So here's what you're going to do. Turn your calculator on, and then we're going to go ahead and click Math. And then click on over till you get to prob. So you're going to have to press over to the right until you get to prob. And then if you see 4 right there, that's where our exclamation point is, right? So we're going to do 5, and then go to math, and then prob, and then the exclamation point, and we can see that's 120. So 5 times 4 times 3 times 2 times 1 is 120. Okay, good deal. So now we want to write the first 5 terms, and we want to begin with n equal to 0. Now we can absolutely go through and plug each of these values in and try to solve. However, that's really, really time consuming. So here's what I suggest you do. Go ahead and take this formula and put it into y equals in your graphing calculator. So I'm going to go to y equals. I'm going to clear out whatever I have in there. I'm going to put in a fraction. 2 to the x power over x. And I have to go math over to prob. Get my exclamation point. So that's what I have right now in my y equals. Now what we're going to do is we're going to go to the table, and the table is going to help us plug in these values right here to get my first 5 terms. Now to make sure that you can put in a value for x instead of it just giving you a table and you just have to take the values that they give you, I want you to go ahead and press second and then press window to get to table set. Okay. Do you see how I have independent set to ask? That's what you want. You want your independent to be set to ask. That means your independent variable, or your x value, you get to ask it, or you get to input that x value, and then it'll just give you your y value. So now we'll go second graph to get to the table, and I'm going to 0, 1, 2, 3, 4, 5. Okay. Oh, I didn't need to go to 5. Oh well. So first of all, one thing I wanted to tell you about is when you have this subscript of 0, a lot of times people will call it a sub naught, or if it's a it's an n sub naught. So the sub means subscript, and naught is the British word for 0. And so when you hear sub naught or not this, blah, 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 that means 0. Okay, cool. Anyways, so I went into my X's and I went ahead and plugged all of those guys in so I don't actually have to go and solve all of these. So let's take a look. All right. A sub naught is going to give me 1. A sub 1 is 2. A sub 2 is also 2. A sub 3 is 4/3. And a sub 4 is 2/3. Good deal. So my advice is when you have to figure out a bunch of terms, go ahead and pop your formula into y equals and use that table to help you out. Okay, now we're going to do a little bit of a proof. When you get to college, if you decide to pursue anything that's pure math, you're going to have to take a lot of number theory courses, and a lot of those are really, really based in proof. So calculus, things like that, there's not proof in that. It's mostly number crunching and things like that. But if you decide to go straight into math, it's going to be a lot of show that this is true or not true, and if it's not true, give a counterexample. So right now, we are going to say this is absolutely true. We want to prove that it's true. So the first thing, let's take a look. We want to show that n factorial over n minus 1 factorial equals n. So let's go ahead and mess with the left side and see if we can get it to match the right, just like when we did verifying identities. Okay. So if we start to think about n factorial, well, we learned about what n factorial was a moment ago. That was n times n minus 1 times n minus 2 all the way down to 2 times 1. So let's rewrite that as n times n minus 1 times n minus 2 times dot 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 all the way down to 2 times 1. And then we will put all of that over. Now we have n minus 1 factorial. Well, to get each next term, we take that first term and we multiply it by that term minus 1. And then we multiply that by that next term minus 1 until we get all the way down to 2 times 1. We want that to be equal to n. All right, so everything in our numerator is being multiplied by each other, and everything in our denominator is being multiplied by each other. That means that I can now divide away terms and cancel them out to equaling 1. So let's take a look. N minus 1 and n minus 1 cancel out. n minus 2 and n minus 2, whoopsies, n minus 2 cancel out, n minus 3 on the bottom, and there would have been an n minus 3 on the top, just we didn't write it. It's accounted for in those 3 little dots in there in the middle. 2 and 2 divide away, 1 and 1 divide away. So what am I left with? N. And that's equal to n. So you can expect to see things like that. A lot of times what my professors did was they called them conjectures. They would give you a statement and they would say prove or disprove, have fun. And it was a good time. All right. So let's talk about what a series is. So a series is the sum of a sequence of numbers. So if we wanted to see a summation of the first n terms or of the 4th term to the 8th term or something like that, here's what's going to happen. This is said the sum from 1 to n. So this guy right here, that's the Greek letter sigma. So that's the symbol for a sum. So if I ever ask you to write something in summation notation, which sounds fun, summation notation, this is what I'm talking about. So the way it's written is it's going to say, I want the sum from the first term to the nth term of this sequence. So they'll give the formula for whatever that sequence is, the explicit formula for it, and then they'll say from 1 to n. So then we'll take each of those terms and add them all up all the way to a sub n. So this guy right here, this is called the index of summation. It's not always I. Sometimes it's a K, sometimes it's another letter, just kind of whatever people feel fun with at the time. This guy down here is your lower limit, and the number up on top is your upper limit. Okay, so now we want to find the summations of these guys. So I want to find the sum from the first term to the 5th term of the sequence 3i. So if I wanted to go through and do this by hand, I would figure out what these terms were. So let's see, 3 times 1 is 3 plus 6, 3 times 2 is 6 plus 3 times 3 is 9 plus 3 times 4 is 12 plus 3 times 5 is 15. Now I think a lot of us, you might start grouping things together to make stuff easier to add together, or you might just run straight to your calculator. And in that moment, wouldn't it just be easier to input this stuff? I mean, this only has 5 terms, so it's not too bad. But what happens when you have 180 terms to add together? That would just suck, and nobody wants to do that. So we are so lucky to have calculators that can do all of this stuff for us. So here's what you're going to do. You are going to go ahead and press math again, and then you can either press down or press up, but you're going to end up at 0. You see where it says summation and then it has that sigma? That's what you're going to select. Now the first thing, it has alpha. You can put any letter you want to. If you want your variable to be I, pick I. If you want your variable to be J, or your letter starts with your first the first letter of your first name is an M, so you want to use an M, I don't care. Do your thing. However, I am so used to my variables being X's, so that's what I'm going to use. I'm going to go ahead and press X right there. And then it says X equals. And then I'm going to plug in everything that I have right there. 1, and then I'm going to press up to get to my upper limit, and that's a 5. And then I'm going to press to the right to go ahead and put my equation into here, so that will be 3x. So my, looks like that in my calculator. And then I'm going to press enter. I end up with 45. Fantastic. So now let's take a look at this next one. We could absolutely go through and plug in each term and say, okay, so 3 squared is 9 plus 1 is 10. 4 squared is 16 plus 1 is 17. 5 squared is 25 plus 1 is 26. 6 squared is 36 plus 1 is 37. And then we could add all of those together. Or for less brain power, we will go back and press math, go up till we get 0 for that summation, and then I'm going to put x equals 3, and then on top there'll be a 6, and then in parentheses I'll have 1 plus x squared. So I just switched out those variables. And now I'll press enter, and I got 90. That will be equal to 90. Okay, so now let's talk a little bit, I went right past them, all the properties of sums and series. So, properties of sums. First of all, if you have a sequence where all it is just a constant number over and over and over and over and over again, so your sequence is 3, 3, 3, 3, 3, 3, 3, 3, 3. If you want to find the sum of the first however many terms, it's just that constant number multiplied by however many terms you have, which makes perfect sense, right? So if you have 3, 3, 3, 3, 3, and you have maybe 3, you want to take from 1 to the 4th term, you're going to have 3, 4, or 4 3s all added together. So you want to take 3 times 4. Also, if you have 2 different series going on inside of here, 2 different sequences that you're going to try to take the sum of, you can split those up into 2 separate sums, if that would be helpful to you at all. Okay, now we have a finite series, and a lot of times it's called a partial sum. So a finite series, remember, infinite means it doesn't have an end, right? So a finite series means that it does have an end. That means that I'm going to have a sum from the first term until some last term. So I might have the 10th partial sum. That means I'm going to take the sum of the first 10 terms. The 95th partial sum means I'm going to take the sum of the first 95 terms. So that's what a finite series is. An infinite series is also exactly what you would think it is. It's going to be where I add up all the terms from the first term all the way up, all the different terms all added together. So it might seem like if I just keep on adding numbers to each other, that's just going to get bigger and bigger and bigger, and it's never going to add to a certain number, right? No. So we'll teach you a little bit more about infinite series and when they do converge and what it means to converge and diverge and all of those things a little bit later. We're just in these first 2 lessons kind of talking about what is a sequence, what is a series. So let's go ahead and find some sums. So for the sum from 1 to infinity of 3 over 10 to the I, find the 3rd partial sum. So this is really asking me for the sum from the first term through the 3rd term because they want the 3rd partial sum of 3 over 10I. Now I can absolutely pop this into my calculator, but I want to go ahead and write these values out and show you how I get this answer, because then when we go ahead and solve this as an infinite series, it's going to make a lot more sense. So if I plug in my values there for I, 3 over, and then I have 10 to the first is 10, plus 3 over 10 squared is 100. Plus 3 over 10 cubed is 1,000. Now I want you to think back when you started learning about decimal places and what those spots on the other side of the decimal point were called. So remember, that first spot was called the 10th space, right? That's because if I take 3 divided by 10, or I have 3/10, it's the same thing as 3/10. You see what I'm saying? The next one was called the hundredths place, right? So 3/100 is 3/100. 3/1000 is 3/1000. Now, if we add 0.3 plus 0.03 plus 0.003, what we're ending up with there is 0.333. So let's keep that in mind as we talk about this. I'm going to box this up as my answer. As we talk about this as an infinite series. So now we really are thinking about it as from the first term through the terms all the way out there to the infinitieth, not a word, term of 3 over 10i. So let's think about what was happening over here. So we had 3/10, then we had 3/100, then we had 3/1000, and then we would end up with, if we kept on going, 3/10,000, and so on, right? So then if we started to think about this, we had 0.3 plus 0.03 plus 0.003 plus 0.0003. So for every new term, every term that I'm going past over here, I'm just adding a new 3 onto the end of that, right? So I would have 3.3333, at least for what we have on the screen right now, but then I keep going, and then if I add another term, I add another 3 onto the end. And when I add another term, I add another 3 onto the end. And I keep adding 3's on infinitely. So really, this is the same thing as 0.3 repeating, which we know 0.3 repeating much better as 1/3. All right, so tomorrow we will talk about arithmetic sequences together. I miss you so much. See you guys later.